Foundation models promise to uncover deeper domain understanding through sequence prediction, akin to Kepler's planetary motion insights leading to Newtonian mechanics. However, evaluating if these models truly capture deeper structures is challenging. We introduced a technique using inductive bias probes to assess if foundation models align with world models, setting the stage for further exploration. Foundation models excel in training tasks, but often lack inductive biases towards world models. For instance, models trained on orbital trajectories struggle with Newtonian mechanics, developing task-specific heuristics that don't generalize. This highlights a key challenge: ensuring models learn underlying structures, not just task-specific patterns. Inductive bias probes test if foundation models have learned world models by examining how they extrapolate from limited data. This approach, inspired by scientific inference, reveals the implicit world model a foundation model uses. It evaluates whether the model's inductive bias aligns with a postulated world model, providing insights into the model's understanding of underlying structures. We evaluate if a foundation model has learned a world model using an inductive bias probe. This probe assesses the model's behavior as it adapts to new tasks, using datasets to output predictions. The world model describes state structure, and the probe compares learned functions to those in the world model, revealing the model's inductive biases. Inductive bias probes involve fitting foundation models to synthetic datasets, comparing learned functions to those in a world model. The no-free lunch theorem suggests learning algorithms must extrapolate to unseen inputs. This approach evaluates if a model's inductive bias aligns with a postulated world model, crucial for understanding model behavior in new tasks. In the special case of binary outputs and finite state spaces, we probe a model's inductive bias. The probe checks if predictions respect and distinguish state, indicating alignment with a postulated world model. This helps evaluate if the model's inductive bias aligns with the world model, crucial for understanding its learning behavior. We explore the inductive bias probe for general outputs, state spaces, and tasks. Extrapolative predictability assesses how well models predict outputs from one input to another. Higher predictability suggests the model extrapolates based on a postulated world model, indicating a deeper understanding of the underlying structure. Testing a transformer's understanding of orbital mechanics reveals it predicts planetary locations accurately, but lacks a Newtonian inductive bias. Fine-tuning shows it recovers nonsensical gravitational laws, indicating task-specific heuristics rather than a coherent world model. This highlights the challenge of aligning model inductive biases with true physical laws. Simulating planetary motion datasets reveals that while models predict trajectories accurately, their inductive biases don't align with Newtonian mechanics. Despite training on sequences of planets orbiting a sun, the models fail to adopt Newtonian principles, instead developing task-specific heuristics. This highlights a gap between accurate predictions and understanding underlying physical laws. Applying inductive bias probes to lattice problems and Othello games reveals models' weak biases toward world models. Better performance on these probes correlates with improved task performance. This suggests that models excel at predicting sequences but struggle to internalize the underlying world model, indicating a reliance on task-specific heuristics rather than a comprehensive understanding. Inductive bias probe results for lattice problems reveal high bias with small state numbers, decreasing as states increase. Notably, transformer models underperform compared to recurrent or state space models. This suggests that as complexity grows, the model's ability to maintain inductive bias diminishes, highlighting the need for more robust architectures in complex state spaces. Models excel at predicting token sequences without learning the underlying world model. They group sequences with distinct states but equivalent legal next tokens. In Othello, models recover legal moves despite board prediction errors, indicating an inductive bias towards legal next token partitions rather than true state representation. Refined metrics reveal that models group distinct states with identical legal next tokens. DIB metrics indicate models extrapolate based on next token partition rather than true state, suggesting an inductive bias toward legal next token partition. This highlights a tendency to prioritize token legality over true state representation, impacting the model's world understanding. Our method diverges from traditional studies by focusing on how models learn world models, not just their fixed representations. We explore whether foundation models encode world models in parametric forms, contrasting with mechanistic interpretability. This approach provides insights into the learning processes, offering a fresh perspective on model behavior and inductive biases. Foundation models excel in sequence prediction but lack inductive bias towards world models. They often rely on coarsened or non-parsimonious representations. Future research should focus on constructing world models implicit in model behavior to enhance their understanding and application.